You'd never guess that in the vast, boundless cosmos, humanity's most powerful telescopes have glimpsed things beyond your wildest imagination. These new discoveries are forcing scientists to rethink whether we truly understand the universe. Now I'm about to show you the bizarre findings from the James Webb Space Telescope that will completely overturn your understanding. Trust me, after watching this video, you'll come to believe what scientists say. We may inhabit a universe entirely different from what we imagined. If you could subscribe to my channel, I'd be truly grateful. Give the video a thumbs up. It not only helps the algorithm recommend more cosmic content to you, but also provides tremendous support for me to create more thrilling journeys across the cosmos. Now close your eyes and relax your body. Let your curiosity roam freely through this wondrous world. I'm also curious to know where you are right now. Please leave your location and time in the comments below. Alright, let's begin. Join us as we explore this wondrous universe alongside the James Webb Space Telescope. The James Webb Space Telescope occupies a precisely balanced position in space. This location is known as the Sun-Earth Lagrange point L2. It sits approximately 1.5 million kilometers from Earth. At this unique orbital point, the gravitational forces of Earth and the Sun achieve perfect equilibrium with the telescope's orbital motion. This allows the telescope to maintain a stable position with minimal fuel expenditure. Lagrange points function as natural gravitational harbors in space. Webb orbits the Sun in sync with Earth at this point, always presenting the same face toward both Earth and the Sun. This configuration enables continuous scientific observation, while maintaining communication links with Earth. Webb's orbital selection was meticulously calculated. This location provides an unparalleled observational environment. Here, the telescope simultaneously avoids the shadows of both Earth and the Moon, while receiving a stable solar power supply. Its massive sunshield remains perpetually positioned between the Sun and the telescope, creating a permanent shadow zone. Protected by the sunshield, the telescope's scientific instruments can be cooled to -266 degrees Celsius, approaching the coldest temperatures in the universe. Such extreme cold is crucial for infrared observations, as it minimizes interference from the telescope's own thermal radiation. Webb is essentially a time machine. This statement has a solid scientific basis. It allows us to directly observe the universe's past and glimpse the face of the infant cosmos. Light takes time to travel across the cosmos. When we gaze at the night sky, we see not the current state of celestial bodies, but the light they emitted at some point in the past. The distant galaxies observed by Webb are so far from us that their light must travel billions of years to reach the telescope. This means that when Webb collects these ancient photons, it is effectively receiving information from the universe's childhood. What we see may be scenes from the first few 100 million years after the universe's birth, the moment when the first stars and galaxies began illuminating the dark cosmos. Webb's time travel capability stems from the expansion of the universe. As space itself stretches, light waves from distant galaxies are stretched out. This phenomenon is known as cosmological redshift. A greater redshift indicates a more distant light source and a deeper journey into the past. Webb's primary mirror consists of 18 gold-coated hexagonal segments that collectively form a 6.5-meter diameter light-gathering surface, with over 7 times the light-gathering power of the Hubble Space Telescope. But Webb's most revolutionary feature is its infrared observation capability. Infrared light possesses longer wavelengths than visible light. This property grants it the ability to penetrate cosmic dust. Interstellar space is filled with vast clouds of gas and dust. These clouds block and scatter visible light, while remaining relatively transparent to infrared radiation. This enables Webb to reveal the true nature of star-forming regions. These areas are typically shrouded in thick dust, making them nearly invisible in the visible light spectrum, yet become clearly visible in infrared light. Webb's infrared vision also enables it to study the most distant celestial objects. Due to the redshift effect caused by cosmic expansion, ultraviolet and visible light emitted by distant galaxies has shifted into the infrared spectrum by the time it reaches Earth. Only telescopes equipped with infrared instruments can capture these signals. The telescope's suite of scientific instruments includes a near-infrared camera, near-infrared spectrograph, mid-infrared instrument, and fine guidance sensor. Working in tandem, these instruments analyze celestial bodies' chemical composition, temperature, density, and motion. One of Webb's key design features is its sunshield. This 5-layer structure spans the size of a tennis court. Each layer is coated with specialized materials to reflect solar heat. Gaps between layers allow heat to escape. This design creates a temperature difference of 300 degrees Celsius between the telescope sides. The telescope's hot side faces the Sun and Earth, reaching temperatures of 85 degrees Celsius. Meanwhile, the cold side remains at -266 degrees Celsius. Stable operation under such extreme temperature variations demonstrates the pinnacle of human engineering achievement. Webb's launch process stands as a miracle in spaceflight history. The telescope had to be folded to fit into the Ariane 5 rocket's payload fairing. It then underwent a complex automated deployment sequence in space. This deployment sequence comprised 289 critical steps. Each step required flawless execution. The entire process from launch to full deployment took 29 days. Tens of thousands of components had to function with precision. Any major error would have resulted in mission failure. This automated deployment process is regarded as the most complex space deployment in history. Its successful execution marks a significant breakthrough in human space engineering. The Webb's designed lifespan is approximately 10 years. However, this estimate may be quite conservative. With precise orbital control and conservative fuel usage, it is likely to operate for 20 years or even longer. Each year, it will bring new discoveries and surprises, continuously expanding the boundaries of our understanding of the universe. In the absolute silence of the cosmos, Webb operates alone and steadily. Its mirror surface resembles a sleeping lotus, quietly blooming in eternal darkness, gathering ancient light from the depths of the universe. This $10 billion precision instrument represents the pinnacle of humanity's spirit of exploration. It is not merely a scientific tool, but a symbol of human ingenuity. Amidst the endless cosmic darkness, it watches over the deep cosmos for humanity, transmitting messages from the dawn of time. Every observation by Webb redefines astronomy. Its data will guide cosmological research for decades to come. In this frigid cosmic void, this magnificent telescope continues its mission, quietly awaiting the unveiling of the next cosmic secret. According to the standard model of modern cosmology, our universe originated from a Big Bang approximately 13.8 billion years ago. This explosion does not refer to violent expansion within existing space, but rather the birth and evolution of space, time, matter, and energy itself. In that initial instant, the universe existed in an unimaginably hot and dense state. It then began to rapidly expand and cool. The post-Big Bang evolution of the universe underwent several critical phases. During the first 380,000 years, the universe was so hot that electrons and atomic nuclei could not bind. The entire cosmos was filled with a fiery plasma of charged particles and photons. Photon collisions with charged particles were constant, preventing free propagation. The universe resembled an opaque, thick soup, until the temperature cooled to approximately 3000 Kelvin. Electrons could finally bind with atomic nuclei to form neutral atoms. This pivotal moment is known as the cosmic recombination epoch. With the formation of neutral atoms, the universe suddenly became transparent to photons. These ancient photons, now free to travel, constitute the cosmic microwave background radiation we detect today. This is the universe's oldest infant photograph, revealing the nearly uniform distribution of matter in the early cosmos. After recombination, the universe entered a prolonged dark age. At this stage, the cosmos contained no stars, no galaxies, and no self-luminous visible celestial bodies. Only a cold, uniform, dark fog composed of hydrogen and helium atoms persisted. Temperatures continued to drop, eventually reaching just a few dozen Kelvin above absolute zero. Within this darkness, minuscule quantum fluctuations in primordial matter density began slowly amplifying themselves under gravity's influence. Regions of slightly higher density attracted more matter. This process resembled water vapor condensing onto dust particles. It required an extremely long time. Gravity worked patiently, gradually pulling and gathering sparse gas clouds together. This dark age lasted hundreds of millions of years, the quietest and darkest period in the entire cosmic evolution. Without subsequent structural formation, the universe would have remained in this state of darkness and uniformity forever. Approximately 100 to 200 million years after the Big Bang, gravity finally gathered sufficient gas in the densest regions. These gas clouds began to collapse under their own gravity. Temperature and pressure within the core steadily increased, until the critical conditions for hydrogen fusion were reached. Thus, the first generation of stars in the universe was born. They are known as population 3 stars. Unlike today's stars, these cosmic pioneers were composed almost entirely of hydrogen and helium, lacking heavier elements. Theoretical models suggest they were typically extremely massive, potentially hundreds of times the mass of the Sun. These behemoths burned their nuclear fuel at an extraordinary rate, with lifespans of only a few million years, before ending in violent supernova explosions, scattering the first heavy elements into the surrounding space. The birth of the first generation of stars brought the first starlight to the universe, officially ending the Dark Ages. This period is known as the Cosmic Dawn. However, these earliest stars alone were insufficient to form mature galaxies. They resembled faint candles lit sporadically across the dark cosmos, extremely distant from one another. These early stars, along with the gas and heavy elements left behind after their deaths, continued to gather and merge under gravitational forces, beginning to form the first protogalaxies. These protogalaxies were small in scale and simple in structure, possibly only thousands of light-years in diameter, and with masses merely 1/1,000,000th that of the Milky Way. Through continuous mergers and gas accretion, these protogalaxies gradually grew. Frequent galaxy mergers occurred in the early universe. Gravitational interactions between galaxies prompted the collapse of gas clouds, triggering new star formation. After billions of years of evolution, the magnificent spiral and elliptical galaxies we observe today, such as the Milky Way, finally emerged. In this traditional cosmic evolution narrative, every process unfolds slowly and incrementally. Gravity alone serves as the sculptor. The construction of cosmic structures requires timescales measured in hundreds of millions of years. Just as a seed needs long years to grow into a towering tree, the growth of cosmic structures likewise demands immense patience and time. According to this widely accepted model, when the James Webb Space Telescope looks back to the very early universe, it should observe a cosmos gradually awakening. The field of view should be filled with numerous small, faint blue young galaxies. They are actively forming the first generation of stars. But overall, they should exhibit a primordial and immature state. These early galaxies should possess specific observational characteristics. Their scale should be relatively small. Their structure should be relatively simple, lacking complex features like distinct spiral arms or bulges. Due to the scarcity of heavy elements, their stellar populations should appear unusually blue, indicating they are in the violent phase of intense first-generation star formation. The overall luminosity of these galaxies should be low. Due to their limited total stellar population, galaxies should be separated by vast stretches of dark space. The entire early universe should present a simple primordial appearance, like a canvas just beginning to be painted, with only the most basic lines and colors. Chemically speaking, these early galaxies should consist almost entirely of hydrogen and helium. Heavy element content should be extremely low, as they had not yet undergone multiple stellar evolutionary cycles. Heavy elements produced by supernova explosions would require time to accumulate and mix within galaxies. This picture is both elegant and logical, based on decades of observational data and theoretical calculations. It paints a clear developmental roadmap for the universe's infancy, predicting a gradual evolutionary process from simple to complex, from small to large, from pure to heavy element rich. Within this expectation, the formation of cosmic structures is an orderly process, following physical laws we can comprehend. Each stage possesses a reasonable timescale. The growth of galaxies and black holes demands considerable patience. Much like biological evolution requires immense time. Yet, as we shall soon observe, the actual scenes captured by the James Webb Space Telescope fundamentally contradict this lullaby we once held as truth. Observational data now reveals a completely different cosmic infancy, one that is more precocious, more complex, and more mysterious than we ever imagined. The dismantling of this traditional model is not a failure of science, but a testament to its progress. It reminds us that the universe is always more wondrous than we can conceive. Each breakthrough in observational tools has the potential to spark a revolution in understanding, and the James Webb Space Telescope is the harbinger of such a revolution. First, find your most comfortable position. Whether lying down or sitting, the key is to let your body fully relax. Now gently close your eyes. Begin to notice your breath. No need to consciously alter its rhythm. Simply observe the natural flow of air. Feel the breath entering your body, then slowly leaving it. Focus your attention on your feet. Feel the sensation of your soles touching the surface. Then gradually shift your awareness upward, through your ankles, calves, knees, and thighs. Feel the weight of each part. Imagine them gradually becoming lighter. Now extend your awareness to your torso. Feel the points where your back meets the support surface. Notice the slight rise and fall of your abdomen with each breath. Let your shoulders sink naturally. Place your arms relaxed at your sides, fingers naturally curved, requiring no effort. Slowly shift your attention to your neck and head. Feel the weight of your head fully supported by the pillow. Your facial muscles relax naturally. Your eyelids gently close. The corners of your mouth lift slightly, forming a natural smile. Now begin deep breathing. Inhale slowly through your nose. Feel the cool air entering your lungs. Then exhale slowly through your mouth. Feel the warm air leaving your body. With each inhale, imagine drawing in the tranquility of the universe. With each exhale, release the tension from your body. As your breath deepens, imagine Earth's gravity gradually weakening. Your body begins to feel light, like a feather, slowly floating upward, lifting off the bed, rising higher, through the ceiling of the room, continuing upward, beyond the clouds, through the atmosphere, into a boundless space of silence. Here, there are no constraints of gravity, no disturbances of sound, only profound darkness and distant twinkling starlight. You are completely weightless, freely floating in the embrace of the cosmos. Now, let us focus our awareness on the James Webb Space Telescope. It hovers silently in deep space, 1.5 million kilometers away, like an eternal observatory, awaiting our arrival. Gently infuse your consciousness into this precision instrument. You are no longer bound by physical limitations. Your vision expands boundlessly. You perceive the universe in infrared wavelengths, those warm glows invisible to the human eye. You become a pure observer, a consciousness transcending time and space. Your thoughts intertwine with the telescope sensors. Your perception synchronizes with its gaze. Upon this tranquil observatory, time seems to lose its meaning. The mirror of the James Webb Telescope is your eye. Its instruments are your senses. Together, you become an organic whole observing the cosmos. In this state, you perceive both visible light and infrared simultaneously. You see the most distant galaxies and the nearest planets. Feel the environment surrounding the telescope. Extreme cold, approaching absolute zero. Extreme silence, not even the sound of molecular collisions. Though this environment is extreme, it brings a profound stillness. Now adjust your breathing. Synchronize it with the telescope's rhythm of collecting photons. Slow and steady. Each breath corresponds to an observation cycle. Each heartbeat corresponds to data transmission. In this state, you are a pure witness, free of judgment, free of expectation, simply open to receiving all information from the cosmos. What we are about to witness may challenge our past perceptions, may fundamentally alter our understanding of the universe. Yet please maintain this moment's calm and openness. If you encounter astonishing sights, simply continue observing. If you discover phenomena defying common sense, simply keep witnessing. If you encounter an existence beyond comprehension, simply accept it with equanimity. The truth of the universe requires no validation from us. Simply is, existing in its authentic form. Our task is to observe and comprehend, not to force the universe to conform to our expectations. Imagine your consciousness as Weber's mirror, calmly reflecting every incoming ray of light, without clinging to any specific image, without resisting any unexpected discovery, merely mirroring the universe's true visage as it is. Let all scientific knowledge temporarily step back. Set aside all theoretical assumptions for now. Face the universe's presentation with a pure, beginner's mind, like an infant opening its eyes to the world for the first time. This open mindset is the most precious spirit of scientific exploration and the highest realm of meditation practice. In a state of non-attachment and non-resistance, we often glimpse the deepest truths. Now, let us continue to deepen our relaxation and feel the connection between your body and the universe. With every breath you take, you exchange energy with the cosmos. With every heartbeat, you resonate with the universe. You are not merely an observer of the cosmos, but an integral part of it. Composed of stellar matter, you are now turning back to examine your own origins. This realization brings not alienation, but a profound sense of belonging. We have never been strangers to the universe, but instruments through which the cosmos comes to know itself. In this state, knowledge ceases to be important. Understanding loses its urgency. The very experience of being is the most precious gift. Let us maintain this state, Prepare to embark on a cosmic voyage. With curiosity, with reverence, with an open mind, to embrace the unfolding cosmic panorama. Whatever you see, whatever you discover, remember this fundamental stance. We are observing the universe's dream, not constructing cages of theory. Now let us take one final deep breath. Inhale the mysteries of the cosmos. Exhale all preconceptions. Prepare to embark on this unprecedented journey. Your consciousness has now fused seamlessly with the James Webb Telescope. Your mindset is perfectly attuned. The history of the universe is about to unfold before you. From the earliest dawn to today's structures, every moment awaits your witness. When you are ready, we can begin moving the telescope. Aim the mirror toward the universe's deepest corners. Begin gathering those ancient photons. Decipher the cosmos's oldest memories. Remember this state. Maintain this tranquility. Preserve this openness. The universe's truths often reveal themselves to the most prepared consciousness in moments of deepest relaxation. According to standard cosmological models and galaxy formation theories, scientists have clear expectations for galaxy formation in the early universe. When the James Webb Space Telescope focuses on the first few 100 million years after the universe's birth, astronomers predict observing a slowly awakening cosmos. This era should be filled with small, faint primordial galaxies. The anticipated characteristics of these early galaxies include extremely limited mass. Theoretical models predict their mass might be only 1,000th or even less than that of the Milky Way. Their diameter is expected to be no more than a few thousand light-years. Their overall brightness should be quite faint, because the total number of stars contained within these galaxies would not be large. The star formation rate should also be relatively low. In terms of structural morphology, these primordial galaxies should exhibit simple and chaotic features. They have yet to develop complex structures like distinct spiral arms or bulges. Their shapes may appear irregular, or manifest as the simplest spherical or ellipsoidal forms. They completely lack the intricate features common in modern galaxies. Regarding stellar population composition, stars in these early galaxies should exhibit an unusually blue hue, indicating they are in the violent phase of first-generation star formation. Due to the near absence of heavy elements, the chemical composition of these stars should remain nearly pristine, composed almost entirely of primordial hydrogen and helium. In spatial distribution characteristics, these primordial galaxies should be widely separated, divided by vast stretches of dark space. Gravitational interactions between them should be quite weak, and large-scale galaxy mergers should remain relatively rare at this stage. According to the most advanced theoretical calculations and numerical simulations, when the universe was only 300 to 400 million years old, the total number of galaxies should have been relatively small. Their average mass should have been quite low, and the overall efficiency of star formation should also have been relatively low. The entire universe at this early stage should have presented an initial and immature state, much like a painting just beginning to take shape, with only the most basic lines and colors, everything in its most primordial form of formation. These expectations are grounded in decades of observational data and theoretical foundations. From the minute fluctuations in the cosmic microwave background radiation to the large-scale structure distribution of the modern universe, this evolutionary model appears to perfectly explain all observed phenomena. Yet, when the first deep-field image data from the James Webb Space Telescope began returning, the spectacle presented to scientists plunged the entire astronomical community into profound shock and bewilderment. At an age of only 2 to 3% of the universe's current age, Webb detected none of the expected faint, nascent galaxy prototypes. Instead, it discovered a staggering number of massive, mature galaxies. These galaxies rivaled or even exceeded the Milky Way in scale. They were not primitive galaxies in their early stages of formation, but fully formed cosmic giants. They possessed complex structures composed of hundreds of billions of stars. Many of these early galaxies had already evolved distinct spiral arm structures and bright bulges at their cores. They displayed characteristics typically observed only in mature galaxies after prolonged evolution. Their spectral signatures clearly indicated the accumulation of significant heavy elements. This signifies that these galaxies had undergone multiple complete cycles of star formation and supernova explosions. Even more astonishingly, these galaxies exhibit exceptionally high luminosities, with some outshining their modern-day counterparts, indicating star formation activity reaching unimaginable intensity, where gas conversion into stars occurs at efficiencies far exceeding theoretical predictions. In terms of spatial distribution, the frequency of these massive galaxies far exceeds theoretical predictions. In nearly every field of view within Webb's deep field images, multiple such objects are discovered. They are not isolated anomalies, but rather a commonplace phenomenon throughout the early universe. To grasp the revolutionary nature of this discovery, a fitting analogy is needed. Imagine archaeologists systematically excavating an ancient human site. Based on all known evolutionary theories and archaeological records, they expect to find only the simplest stone tools and rudimentary dwellings, in strata corresponding to millions of years ago. Yet, during their meticulous excavation, they are stunned to uncover remnants of skyscrapers, complex highway systems, and highly developed urban infrastructure. Such a discovery completely contradicts the fundamental laws of human civilization's development. Or consider meticulously inspecting a newborn's cradle, only to find a fully mature adult lying within. This adult not only possesses a fully developed physique, but also commands complex skills and profound knowledge. Such a scene utterly contradicts the normal laws of growth and development. Webb's observational results are precisely this. In the cosmic cradle, we expected to find embryonic galaxies, yet we discovered fully mature adult galaxies. This metaphor vividly reveals the vast chasm between observational evidence and theoretical predictions. Even more thought-provoking is the ubiquity of these anomalous galaxies. Initially, astronomers speculated these might be rare outliers, perhaps observational errors, or illusions caused by some unknown natural phenomenon. But as Webb's observational data accumulated, this hope quickly faded. These massive, mature galaxies are not rare anomalies in the cosmos. They are ubiquitous in the early universe, their numbers far exceeding what statistical chance alone could explain. In every deep field image captured by Webb, regardless of the telescope's cosmic orientation, countless such galaxies are discovered. Detailed statistical analysis reveals, in the early universe at redshifts greater than 10, the number of such mature galaxies is tens of times higher than theoretical predictions. They are not rare exceptions, but a universal norm. This indicates we are not observing a coincidence, but the true face of the early universe. A cosmic landscape entirely different from our imagination is slowly unfolding. In this new picture, the formation rate of cosmic structures is much faster and far more efficient. This discovery profoundly impacts galaxy formation theories. Traditional hierarchical models propose galaxies gradually grow through slow mergers and accretion processes, starting from small structures, evolving into large galaxies over billions of years. Webb's observations directly challenge this core assumption. If the universe could produce such massive galaxies, merely hundreds of millions of years after its birth, then the process of galaxy formation must be far more rapid and efficient than we imagined. This forces astronomers to rethink how gravity operates in the early universe, or consider whether other, as yet unrecognized physical processes exist. From the perspective of star formation, these discoveries are equally perplexing. For a galaxy to accumulate such enormous stellar mass requires converting primordial cosmic gas into stars with extraordinary efficiency. In our familiar modern universe, star formation is constrained by multiple feedback mechanisms and operates at relatively low efficiency. The early universe evidently harbored some special mechanism, enabling gas to condense into stars with unprecedented speed and efficiency. The nature of this mechanism remains an unsolved mystery, possibly higher gas densities, a different stellar mass function, or entirely unknown physical processes. These giants of the early universe also pose new questions for dark matter research. According to existing models, the growth of dark matter halos requires sufficient time to gradually form larger-scale structures. Through hierarchical clustering, the existence of these massive galaxies indicates that the dark matter halos they reside in must have accumulated astonishing masses in an extremely short time. This raises fresh questions about the nature and behavior of dark matter itself. Perhaps dark matter behaved differently in the early universe than we understand today, or some special mechanism accelerated the formation of dark matter structures. Particularly noteworthy is that the chemical enrichment levels of these early galaxies also far exceed expectations. Their spectra show pronounced heavy element signatures, indicating they have undergone multiple generations of stellar evolution and completed their chemical evolution within an extremely short time frame. The timescale has become the greatest mystery of our era. From the birth of the universe to the mature galaxies we observe today, only a few 100 million years elapsed. According to traditional theories, this duration is insufficient even for the first generation of stars to complete their life cycles, let alone form such massive galactic structures and achieve chemical enrichment. This temporal contradiction represents one of the most pressing challenges in contemporary cosmology. These observations from the James Webb Space Telescope do more than add a few new objects to the cosmic landscape. They shake the very foundations of galactic astronomy, forcing us to re-examine the fundamental processes of cosmic structure formation. Each newly discovered massive early galaxy poses deeper questions about the initial conditions of the universe, about the nature of matter, about the essence of gravity, about the meaning of time itself. As we gaze upon these galaxies, fully matured at the dawn of the cosmos, we confront one of contemporary astrophysics' most profound enigmas. How did the universe accomplish the construction of these grand structures in such a fleeting span of time? The answer may lie hidden within deeper physical laws. It may involve reinterpreting fundamental physical constants, or revising our understanding of cosmic expansion history, and could even point toward entirely new realms of physics. The James Webb Space Telescope's ongoing observations are providing us with an ever-growing array of data points. Each newly discovered early galaxy offers a crucial clue to unraveling this cosmic puzzle. As our observational sample expands, we may piece together the true picture of the universe's early evolution. Throughout this process, we must maintain a completely open mindset, prepared to accept a cosmic history that may differ entirely from our expectations. Scientific progress often stems from unexpected discoveries, and these surprises brought by the James Webb Telescope may be guiding us toward a deeper understanding of the universe. the existence of mature galaxies in these early universes not only alters our understanding of the timescale for galaxy formation, but also compels us to rethink the fundamental laws governing cosmic evolution. In this process of rediscovery, each new observational data point propels us closer to the truth within the standard theoretical framework of cosmology. The formation of supermassive black holes is understood as an extremely long and gradual process. These most mysterious behemoths of the cosmos can reach masses millions or even billions of times that of the Sun. They are believed to have formed through multiple physical mechanisms over billions of years of gradual accretion. According to current mainstream theoretical models, the initial seeds of supermassive black holes may originate from the demise of the first generation of massive stars in the universe. These early stars could have masses hundreds of times greater than the Sun, with lifespans of only a few million years. When they concluded their brief yet brilliant lives, they would form stellar mass black holes with masses tens to hundreds of times that of the Sun through gravitational collapse. Another potential seeding mechanism involves direct gravitational collapse of high-density gas clouds in the early universe. Under specific cosmic conditions, dense primordial gas clouds might bypass star formation stages and collapse directly into larger black hole seeds. This process could generate intermediate mass black holes reaching thousands or even tens of thousands of solar masses. A further theory proposes that dense star clusters in the early universe could form larger black hole seeds. In extremely dense stellar environments, dynamic friction and collisions between stars may lead to the formation of massive black holes in central regions. However, even with these specialized seeding mechanisms, growing into the supermassive black holes observed still requires a long and sustained growth process. Black hole growth primarily occurs through two fundamental pathways. First, through mergers with other black holes or compact objects. Second, through accretion of surrounding gas and matter. During accretion, before matter crosses the event horizon, it forms a superheated accretion disk, which releases immense energy through friction and gravity, converting part of its rest mass into radiation. This process not only increases the black hole's mass, but also produces one of the brightest phenomena in the universe. However, the growth rate of black holes is constrained by fundamental physical laws. The Eddington limit defines the maximum accretion rate. This limit arises from the equilibrium between radiation pressure and gravitational force. When the accretion rate exceeds this threshold, the resulting radiation pressure prevents further material from falling into the black hole. This fundamental constraint implies that even under optimal conditions, exponential growth of black hole mass requires timescales measured in hundreds of millions of years. According to standard disk accretion models, a seed black hole with solar mass would require at least hundreds of millions of years of continuous accretion to grow to 1 billion solar masses. Beyond the Eddington limit, other factors constrain black hole growth, including limitations on gas inflow rates, self-regulation through feedback processes, and the coevolution of black holes with their host galaxies. These factors collectively determine the ultimate mass a black hole can attain, based on theoretical calculations and numerical simulations. When the universe was less than 1 billion years old, black hole masses should theoretically not exceed tens of thousands of solar masses. Even the most optimistic models, considering the most efficient accretion and merger processes, struggle to explain the existence of supermassive black holes, weighing hundreds of millions of solar masses in the early universe. However, observations from the James Webb Space Telescope have fundamentally challenged this traditional understanding. Webb discovered a supermassive black hole, weighing 800 million solar masses. This quasar, designated J0313-1806, not only possesses staggering mass, but is also undergoing intense accretion. The observational characteristics of this ancient quasar astonished astronomers. Its surrounding hot accretion disk emits exceptionally brilliant light, outshining its host galaxy by thousands of times, making it one of the brightest objects in the early universe. By analyzing the broad emission lines in its spectrum, scientists were able to precisely calculate the black hole's mass and accretion rate. Even more puzzling, J0313-1806 is not an isolated case. As data from the James Webb Space Telescope accumulates, astronomers are discovering an increasing number of similar massive black holes in the early universe. When the universe was less than 1 billion years old, multiple supermassive black holes, each weighing hundreds of millions of times the mass of the Sun, already existed. These discoveries include multiple active galactic nuclei with redshifts exceeding 7.5, each harboring black holes weighing hundreds of millions of solar masses. Some even exhibit accretion rates approaching the Eddington limit. These observational facts completely overturn traditional theories of black hole growth. To grasp the revolutionary nature of this discovery, consider a vivid analogy. Suppose we compress the 13.8 billion-year history of the universe into the lifespan of an 80-year-old human. By this scale, the universe at 700 million years would correspond to an 8-year-old child. The emergence of a 800 million solar mass black hole within such a young universe is akin to discovering the fully mature brain of an 80-year-old adult inside the body of an 8-year-old child. This brain is not only structurally complete and fully functional, but also in a state of heightened mental activity, possessing the full knowledge reserve and cognitive abilities of an adult, completely defying normal growth and development patterns. Even more astonishingly, this phenomenon is not an isolated case, but is found in every 8-year-old child. Webb's discovery is precisely this. During the universe's infancy, cosmic structures that should only form during the mature phase appeared, and this phenomenon was quite common in the early universe. This puzzle gave rise to multiple new theoretical hypotheses. One perspective suggests that sustained super-Eddington accretion processes may have existed in the early universe, allowing black holes to accrete matter at rates far exceeding theoretical limits. This ultra-efficient accretion might be driven by special gas supply mechanisms, or result from unique physical processes under the extreme conditions of the early universe. In super-Eddington accretion models, accretion disks may exhibit unique geometric configurations, or employ mechanisms to efficiently dissipate excess radiation pressure, allowing matter to fall into black holes at accelerated rates. Some theories propose more efficient angular momentum transfer mechanisms existed in the early universe, or that accretion disks expelled excess energy via outflows. Another hypothesis proposes that the early universe may have directly formed seed black holes of exceptionally large masses. These seed black holes could reach masses of hundreds of thousands of solar masses. They formed through direct gravitational collapse of primordial gas clouds, completely bypassing the intermediate stellar mass black hole stage. This direct collapse mechanism requires the existence of special high-density environments in the early universe, and necessitates effective cooling mechanisms to prevent fragmentation. Theoretical speculations also suggest that fundamental physical constants in the early universe may have differed from those measured today, or that undiscovered particle interaction mechanisms existed. These factors could have significantly accelerated black hole growth, enabling them to accumulate immense mass within extremely short timescales. Though radical, this perspective offers a compelling explanation for observed timescale discrepancies. An even more thought-provoking perspective suggests that these supermassive black holes may be relics from an earlier cosmic epoch, and could even be directly linked to quantum fluctuations during the period of cosmic inflation. This viewpoint implies that black hole formation may not fully follow the known timeline of cosmic evolution, and that primordial black hole components might exist. Particularly noteworthy is that observational characteristics of these early supermassive black holes reveal a close connection between them and their host galaxies. The correlation between black hole mass and galactic bulge mass was established in the very early universe. This indicates that black holes and galaxies may co-evolve, with profound physical connections in their growth processes. From an observational technology perspective, the Webb telescope's capability to detect these primordial black holes is equally noteworthy. Quasar spectra contain rich physical information. By analyzing the width of broad emission lines and the characteristics of the continuum spectrum, astronomers can precisely calculate the black hole's mass and accretion rate. These observational data provide an unprecedented window into understanding the earliest structure formation in the universe. The high sensitivity and resolution of the James Webb Space Telescope enable scientists to detect distant quasars previously beyond observation. Its mid-infrared instrument is particularly crucial because high redshifts shift emission lines originally visible in the ultraviolet and optical bands into the infrared spectrum. The Webb telescope is specifically designed for infrared observations. Detailed studies of these primordial black holes have also revealed another puzzle. Their accretion disks exhibit unusually high efficiency, with some approaching the theoretical maximum of 30%. This far exceeds the accretion efficiency observed in most active galactic nuclei in the modern universe. It suggests that the process of matter falling into black holes in the early universe may have been more efficient than what we observe today. Furthermore, the spectra of these early quasars reveal abundant heavy element signatures, including carbon, nitrogen, and oxygen. These elements can only be synthesized within massive stars and dispersed into interstellar space via supernova explosions. This implies that as black holes formed, their surrounding environments had already undergone intense star formation and evolution. This observational fact further compresses the available timescale. Not only must black holes form and grow within an extremely short time frame, but their host galaxies must also complete chemical enrichment within the same time frame. This dual temporal constraint significantly complicates theoretical interpretations. Deeper spectral analysis reveals that gas surrounding these primordial black holes exhibits unique kinematic properties. Outflow velocities exceed 1/10 of the speed of light, indicating intense feedback processes. Such feedback may have moderated black hole growth to some extent, yet it introduces new complexities to understanding their rapid formation. These discoveries from the James Webb Space Telescope not only redefine our understanding of the timescale for black hole formation, but also compel us to reconsider the uniqueness of the early cosmic environment. In the first few 100 million years after the universe's birth, special physical conditions may have existed, enabling matter to coalesce toward cosmic density peaks with unprecedented efficiency. This highly efficient matter accumulation mechanism may have simultaneously driven the rapid formation of supermassive black holes and massive galaxies. The feedback mechanisms between black holes and galaxies likely operated differently in the early universe compared to the modern cosmos, forming a self-regulating growth process. The latest numerical simulations attempt to reproduce these observational phenomena. But even with the most advanced simulation codes and computational resources, it remains challenging to reproduce such massive black holes at such early epochs within the standard cosmological framework. reproduce such massive early black holes. This suggests we may be missing some crucial physical processes. The discovery of these primordial cosmic behemoths reminds us that the universe's complexity far exceeds previous imaginings. The existence of mature structures in the infant universe challenges our fundamental understanding of cosmic evolution. Each new discovery compels us to refine existing theoretical models. In our gradual approach toward the cosmic truth, we may need to embrace a more wondrous and intricate cosmic landscape. The physical laws within this vision may exhibit distinct characteristics across cosmic epochs, or reveal novel physics yet to be discovered. Research on primordial supermassive black holes has become a frontier in modern astrophysics. Ongoing observations by the James Webb Space Telescope will provide further clues about the origins of these cosmic behemoths. As data accumulates, we may be able to distinguish between different formation models and ultimately solve this cosmological puzzle. Regardless of the mechanism, the final answer points to the existence of these early supermassive black holes has forever altered our understanding of cosmic structure formation. They are not only the most powerful gravitational engines in the universe, but also crucial probes for exploring the early history of the cosmos. Throughout this exploration, scientists maintain an open-minded approach, prepared to embrace potentially unexpected theoretical breakthroughs. For history has shown us, the universe consistently surpasses our wildest imaginings, and these voracious behemoths of the primordial cosmos serve as vital guides leading us toward new insights. As more data accumulates and theories evolve, we may need to establish an entirely new paradigm for black hole formation. This new framework could unify the extreme physical conditions of the early universe, the anomalous efficiency of black hole growth, and the coevolution of galaxies and black holes will provide a more complete picture of cosmic structure formation. This exploration concerns not only the formation of black holes themselves, but also our understanding of the fundamental laws of the universe. Each observational data point pushes us closer to the ultimate answers. In this grand scientific quest, the James Webb Space Telescope stands as one of our most powerful tools. According to the standard model of modern cosmology, the composition of matter at the universe's birth was remarkably simple and pure. Within the first few minutes after the Big Bang, through the process of primordial nucleosynthesis, only the three simplest elements were produced in the cosmos. Hydrogen accounted for approximately 75% of all atoms. Helium constituted about 25%. Along with trace amounts of lithium, no heavier elements existed beyond these. The universe during this era was chemically unprocessed, existing in a primordial state. All elements heavier than lithium, from carbon and oxygen, the building blocks of life, to iron and nickel, the primary constituents of Earth's core, to precious metals like gold and silver, must be created through nuclear fusion within stars. This process, known as stellar nucleosynthesis, is the core mechanism of cosmic chemical evolution. Within the cores of stars, under conditions of extreme heat and pressure, hydrogen nuclei overcome their mutual electromagnetic repulsion to undergo nuclear fusion, forming helium and releasing immense energy. This process not only fuels the star's radiation, but also initiates the first step in cosmic element synthesis. In more massive stars, once hydrogen fuel is exhausted, the core undergoes further collapse to reach higher temperatures, triggering helium burning. Helium nuclei fuse to produce carbon, which then undergoes a series of complex nuclear reactions to generate heavier elements like oxygen and neon. This process is known as the alpha process. However, A star's nuclear synthesis factory can only produce elements up to iron. Iron possesses the highest nuclear binding energy. Heavier elements require energy-consuming reactions to form. These heavy elements primarily originate from supernova explosions during the final stages of massive stars' lives, or from extreme astrophysical events like neutron-star mergers. Only under the immense energy and neutron flux environment generated by supernova explosions, mechanisms like rapid neutron capture enable the formation of heavy elements like gold, silver, and uranium. This process demands extreme environmental conditions, temperatures reaching billions of kelvins, and extremely high neutron fluxes. Supernova explosions not only produce heavy elements, but also eject these newly synthesized elements into the interstellar medium. They mix with primordial gas to become the raw material for the next generation of stars and planetary systems. This process is called cosmochemical enrichment. From stellar formation to the eventual ejection of heavy elements into the interstellar medium via supernova explosions requires an extended timescale. A massive star's life cycle from birth to death may span millions to tens of millions of years, with the exact duration dependent on the star's mass. These ejected heavy elements require time to mix with primordial gas before becoming the raw material for the next generation of stars and planetary systems. According to theoretical estimates, forming a galaxy with significant metallicity requires at least hundreds of millions to billions of years of stellar formation and evolutionary cycles. The entire chemical evolution process can be viewed as a cycle. First-generation stars form from primordial gas. They produce heavy elements through nucleosynthesis. These elements are ejected into space via supernova explosions. This enriched gas forms second-generation stars. The cycle repeats. Each generation of stars increases the universe's heavy element content. Thus, when astronomers pointed the James Webb Space Telescope toward the early universe, they anticipated observing chemically pristine galaxies. These galaxy spectra should reveal strong hydrogen and helium features, while lacking spectral lines of heavy elements. They expected to find a universe dominated by first-generation stars. These primordial stars were composed almost entirely of primordial gas, their spectral characteristics markedly different from modern stars. They should be extremely massive and fiercely hot, emitting intense ultraviolet radiation, with lifespans of only a few million years. Yet Webb's observations completely overturned this expectation. At a cosmic age of merely 400 million years, Webb detected spectral features rich in heavy elements. In a galaxy designated GNZ11, Webb's high-resolution spectrograph clearly detected emission lines from oxygen. Their intensity indicates the galaxy had undergone significant chemical enrichment. Even more astonishingly, in other early galaxies, heavy elements like neon and iron, which require multiple generations of stellar evolution to form, were detected. Synthesizing these elements demands specific nuclear processes and sufficient time to complete stellar life cycles. To grasp the challenge of this discovery, consider an apt analogy. Imagine an archaeologist excavating a site believed to be humanity's earliest settlement. Based on all known historical records, he expects to find the simplest stone tools and most primitive traces of habitation. Yet during the excavation, he discovers refined metal tools, intricate pottery, and even alloyed artifacts and glassware. This doesn't merely suggest human civilization began earlier than imagined. It indicates a leap from the Stone Age to the Metal Age occurred within an extremely short time frame. Technological advancement proceeded at an astonishing pace, completely disrupting the expected developmental trajectory. Webb's discovery mirrors this phenomenon. In the chemical evolution of the universe, We anticipated encountering a chemical stone age. Instead, we discovered a civilization that had already mastered metallurgy. This analogy vividly reveals the vast gap between observational findings and theoretical expectations. The early emergence of these heavy elements poses a severe challenge to stellar evolution theory. To produce detectable amounts of oxygen within a galaxy requires numerous massive stars to complete their entire life cycles, from star formation to eventual supernova explosions. This process, even for the shortest-lived massive stars, takes millions of years. Furthermore, sufficient time is required to thoroughly mix these heavy elements into the interstellar medium and form a new generation of stars with significant metallicity. The observation of abundant oxygen only 400 million years after the universe's birth implies that the first generation of stars must have formed rapidly in the very early universe and completed their entire cycle of birth, death, and material recycling within a short time frame. The detection of heavier elements like iron presents even greater challenges. Iron synthesis typically requires specific types of supernova explosions, whose progenitor stars have longer evolutionary timescales. The presence of iron when the universe was only hundreds of millions of years old suggests that star formation and evolution rates in the early universe may have far exceeded our current theoretical models. Webb's observations also reveal that the heavy element abundance patterns in these early galaxies differ significantly from those in contemporary galaxies. The relative abundances of certain elements are unusually high, which may suggest that the initial mass function of stars in the early universe differed from the modern one. There may have been more massive stars, or the mechanisms and frequency of supernova explosions differed from today. Particularly puzzling are the observational characteristics of nitrogen. Nitrogen is primarily produced through the evolution of intermediate mass stars, requiring specific nucleosynthetic pathways. The detection of abundant nitrogen in the early universe indicates not only the rapid evolution of massive stars, but also the presence and evolution of intermediate mass stars. These chemical signatures also provide new clues for understanding galaxy formation. A galaxy achieving such rapid chemical enrichment suggests extremely intense and efficient star formation activity within it. The rate at which gas converted into stars must have far exceeded that in modern galaxies. This may be linked to the higher gas density in the early universe and more frequent galaxy merger events. From an observational technology perspective, the Webb telescope's spectral analysis capabilities are pivotal. By analyzing the emission and absorption line characteristics of specific elements, scientists can determine their abundance, temperature, density, and other physical conditions. These spectral data act as the chemical fingerprints of the universe, recording the history of galaxy formation and evolution. Studies of carbon are particularly revealing. Carbon is primarily produced by intermediate mass stars. Its presence indicates contributions not only from massive stars, but also from the nucleosynthesis processes of lower mass stars. This suggests a complete stellar mass distribution already existed in the early universe. The oxygen-to-iron ratio provides another crucial clue. This ratio can reveal the distribution of supernova types and the characteristics of the stellar initial mass function. Anomalous ratios observed in early galaxies may point to star formation environments distinct from the modern universe. From a broader perspective, the prevalence of heavy elements in the early universe holds significant implications for studying cosmic reionization. These primordial stars and the heavy elements they produced may have been pivotal drivers in transitioning the universe from a hydrogen-dominated state to ionization. The presence of heavy elements also influenced gas cooling processes, Metallic elements facilitated faster cooling and collapse of gas clouds through radiative cooling mechanisms. This likely formed a positive feedback loop that accelerated subsequent star formation. These chemical observations from the James Webb Space Telescope paint a radically different picture of the early universe compared to previous understandings. In this scenario, the chemical evolution of the universe proceeded at an astonishing pace. Shortly after the first stars illuminated the cosmos, heavy elements began accumulating rapidly, transforming the universe's chemical composition. This discovery not only challenges our understanding of the timescales for star and galaxy formation, but also compels us to rethink the efficiency of matter cycling and energy transfer in the early universe. Traditional chemical evolution models may require significant revisions, or we must accept that special physical conditions existed in the early cosmos. Some theoretical models now propose that more efficient star formation mechanisms may have existed in the early universe, or that supernova explosions were more frequent and violent. Another possibility is that the mass distribution of early stars was skewed toward the high mass end, significantly accelerating the rate of element synthesis and release. Other theories suggest unknown nucleosynthesis processes may have occurred in the early universe, or contributions from exotic objects like primordial black holes. Though unconfirmed, these hypotheses demonstrate the scientific community's efforts to unravel this mystery. When we analyze these spectra from the cosmic dawn, we are deciphering the universe's earliest chemical chronicles. Each absorption and emission line narrates the saga of stellar birth and death. These cosmic epics evidently began earlier and unfolded faster than we imagined. This realization will guide us toward a deeper understanding of cosmic evolution. Perhaps within the unique conditions of the early universe lie physical laws yet unknown to us, awaiting discovery and interpretation. Each accumulation of observational data brings us closer to this goal. The puzzle of cosmic chemistry is not merely a specialized problem, but a key to comprehending the universe's overall evolution. The evolution of chemical elements, the formation of galaxies, the growth of black holes, and the establishment of the large-scale structure of the universe are profoundly interconnected. Solving this puzzle will help us construct a more complete picture of cosmic evolution. Notably, the James Webb Space Telescope's observations have also revealed the uneven distribution of heavy elements. In early galaxies, certain regions exhibit significantly higher element abundances than others, suggesting that chemical enrichment processes in the early universe were not uniform, but occurred in localized hotspots. These chemical hotspots may have been driven by exceptionally intense star formation activity, or associated with specific types of supernova explosions. This non-uniformity provides crucial clues for understanding the star formation history of the early universe. Furthermore, the ratios between different elements contain rich information. For instance, the carbon-oxygen ratio can reveal details of stellar nucleosynthesis processes, while the abundance of iron peak elements can inform us about supernova explosion mechanisms. Through these detailed chemical analyses, we can not only understand what nucleosynthesis processes occurred in the early universe, but also infer the physical conditions under which these processes took place, such as temperature, density, and timescales. Particularly intriguing is the detection by Webb of unusually high nitrogen-oxygen ratios in some of the most distant galaxies. This phenomenon, rarely seen in the modern universe, may suggest the existence of special types of stars in the early universe, or distinct stellar evolutionary pathways. Another perplexing discovery is the distribution patterns of certain heavy elements in early galaxies. exhibiting remarkable homogeneity, contradicting our expectations of local chemical enrichment patterns. This may indicate the existence of some large-scale mixing mechanism, or suggest these elements have alternative origins. Resolving these chemical puzzles may require us to move beyond traditional stellar nucleosynthesis models and consider more exotic physical processes, such as primordial nucleosynthesis potentially producing some heavy elements, or the existence of unknown nuclear reaction pathways in the early universe. Some theorists have proposed dark matter decay in the early universe, or other physics beyond the standard model, as potential contributors to element synthesis. Though unconfirmed, these hypotheses demonstrate the creative thinking required to solve this puzzle. As the James Webb Space Telescope continues gathering more precise spectral data, we can expect to gradually unravel these chemical mysteries. Each new spectral observation holds the potential for fresh discoveries and challenges. Throughout this journey, we must maintain an open mindset, prepared to embrace answers that may defy our expectations. After all, the history of the cosmos always proves richer and more diverse than our wildest imaginings. Ultimately, understanding these early cosmic chemical phenomena will help us address deeper questions about the formation of the universe's initial structures, the birth of stars and galaxies, and our place within the cosmos. Each chemical analysis of distant galaxies represents a crucial step in exploring cosmic history. Through these studies, we are gradually unveiling the mysteries of the universe's earliest moments and reconstructing its evolutionary journey from simplicity to complexity. This exploration not only expands the frontiers of our knowledge, but also deepens our understanding of natural laws. On the path to solving the universe's chemical puzzles, every discovery is invaluable, and every question merits thorough investigation. Dark matter stands as one of the most enigmatic and pivotal concepts in modern cosmology. It is a mysterious substance that does not participate in electromagnetic interactions. Consequently, it cannot be directly observed through any band of electromagnetic radiation. However, through its gravitational effects, scientists are confident that dark matter constitutes approximately 85% of the total matter in the universe. This conclusion is grounded in multiple independent observational evidences. The existence of dark matter was first inferred through studies of galaxy cluster dynamics. Astronomers discovered that the gravitational force of visible matter within galaxy clusters was insufficient to maintain their dynamic equilibrium. A substantial amount of invisible matter must exist to provide additional gravitational force to explain the observed velocities of galaxy motion. Subsequent observations of spiral galaxy rotation curves provided more direct evidence. The rotational speeds of stars and gas far from the galactic center did not decrease with distance as expected, but remained constant or even increased slightly. This indicates galaxies are surrounded by a vast dark matter halo, whose mass distribution far exceeds that of visible matter. Gravitational lensing observations further confirmed dark matter's existence. When light from distant galaxies passes through foreground celestial bodies, the degree of light bending far exceeds effects attributable to visible matter, indicating substantial invisible matter contributing gravitational force. Precise measurements of the cosmic microwave background radiation provide the strongest evidence for dark matter's existence. The specific patterns of temperature fluctuations can only be plausibly explained by the presence of dark matter. These independent observational evidences collectively point to the same conclusion. According to the widely accepted cold dark matter model, dark matter particles should move at relatively slow speeds. They primarily interact through gravity. with negligible interactions with other matter. This property enables dark matter to form the initial framework of cosmic structures. The formation of dark matter structures follows a hierarchical clustering model. This implies that small dark matter halos form first, gradually assembling into larger structures through mergers and accretion. This process requires immense timescales, due to the relatively weak gravitational force, allowing sufficient time for matter accumulation during the first few 100 million years after the universe's birth. Dark matter halos were relatively small and less dense. They grew slowly, providing gravitational potential wells for subsequent galaxy formation. Gas gradually cooled and accumulated within these dark matter wells, ultimately forming stars and galaxies. Numerical simulations indicate that at approximately 500 million years after the Big Bang, the mass of dark matter halos should primarily range between 10 and 10 solar masses. These relatively small dark matter structures would subsequently merge to form larger, more massive structures. The density distribution of dark matter halos should follow a specific profile: higher density at the center, gradually decreasing outward. This distribution characteristic is determined by the nature of dark matter and influences the distribution and evolution of visible matter within them. However, observational data from the James Webb Space Telescope has posed a severe challenge to this classical picture. By analyzing gravitational lensing effects produced by early galaxies, Webb discovered that the dark matter halos surrounding these young galaxies exhibit masses and densities far exceeding theoretical predictions. These dark matter halos appear to have formed completely in an instant, displaying a maturity equivalent to structures that have evolved over billions of years. Their mass distribution is exceptionally concentrated. The intensity of the gravitational lensing effect indicates that dark matter clustering far exceeds model predictions. To grasp the significance of this anomaly, consider an architectural analogy. Imagine cosmic structure formation as constructing a skyscraper. Per conventional theory, we should first lay small foundations and gradually expand to form the solid base supporting the skyscraper. Yet Webb's observations reveal, on the cosmic construction site, we observe a fully completed foundation, sufficient in scale and strength to support a skyscraper, while according to the construction schedule, workers have only just begun pouring the first concrete slab. Webb primarily employs gravitational lensing to detect this phenomenon. When light from distant galaxies passes through dark matter halos near foreground galaxies, it bends and magnifies. By precisely measuring this distortion, astronomers can reconstruct the mass distribution of dark matter halos. In multiple early galaxies, Webb observed unusually intense lensing effects, indicating these dark matter halos possess masses several times greater than theoretical predictions. Their density distributions also exhibit abnormal concentration, with central densities far exceeding theoretical expectations. Particularly noteworthy is the anomalous feature in the density profiles of these dark matter halos. Their central slopes are significantly steeper than predicted. This suggests dark matter may have accumulated differently in the early universe. More perplexing still is the ubiquity of these massive dark matter halos. They are not rare occurrences in the early cosmos, but rather a widespread phenomenon. In multiple early galaxy samples observed by the Webb Deep Field, over 1/3 of galaxies exhibit this anomalous dark matter distribution. This statistical result rules out the possibility of chance occurrence and indicates we are dealing with a systematic phenomenon. Dark matter structure formation in the early universe appears to follow different rules than we anticipated. This discovery has profound implications for the study of dark matter properties, If dark matter is indeed cold, meaning its particles move relatively slowly, then, according to standard cosmological simulations, such massive and dense dark matter halos should not have formed in the early universe. Webb's observations may suggest that the nature of dark matter in the early universe differed from our current understanding. One possible explanation is that dark matter may possess some form of self-interacting mechanism. Self-interacting dark matter models hypothesize that beyond gravity, dark matter particles engage in additional forms of interaction. This interaction enables dark matter to aggregate more efficiently, rapidly forming massive dark matter halos in the early universe. Another hypothesis suggests dark matter may not be entirely cold. A portion may possess small but non-zero thermal velocities. This is termed the warm dark matter model. However, even within such models, explaining the massive dark matter structures observed by Webb remains challenging. Theories also propose the early universe's expansion history may have been more complex. Unknown physical processes may have accelerated dark matter structure formation. For instance, the influence of early dark energy or other scalar fields, which could have altered the rate of structure formation. From an observational technology perspective, Webb's capability to probe dark matter distribution in the early universe is revolutionary. Traditional dark matter detection methods have been largely confined to relatively late-stage cosmology. Webb, for the first time, enables us to directly study the distribution characteristics of dark matter during the cosmic dawn. Webb's high-resolution infrared observation capability allows it to detect previously unobservable distant galaxies. By analyzing the gravitational lensing effects of these galaxies, we can reconstruct the distribution patterns of dark matter in the early universe. Notably, the early dark matter halos observed by Webb exhibit unusually regular shapes, which differ from the expected morphology of halos in the later universe, potentially suggesting distinct dynamical properties for early dark matter. The existence of these exceptionally massive dark matter halos also correlates with other anomalies discovered by Webb: the rapid formation of mature galaxies in the early universe, and the premature emergence of supermassive black holes may both be closely tied to this anomalous dark matter distribution. Dark matter halos provide the deep gravitational potential wells necessary for galaxy formation. Their exceptionally massive scale could explain how galaxies accumulated such vast amounts of gas in extremely short timescales and rapidly formed stars. This offers crucial clues for unraveling other early universe mysteries. Further research indicates that the density distribution profiles of these primordial dark matter halos also exhibit anomalous characteristics. Their central densities exceed theoretical predictions, potentially influencing the structure and evolution of galaxies within them. High-density dark matter environments may promote more efficient gas cooling and collapse, thereby accelerating star formation processes. This positive feedback mechanism could explain the exceptionally efficient star formation observed in the early universe. Observations of dark matter substructure also offer new insights. According to the cold dark matter model, substructures should abundantly exist within dark matter halos. However, Webb's observations indicate that the number of substructures in early dark matter halos may be lower than expected. This discovery may support certain modified dark matter models, or suggest that dynamical processes in the early universe differed from those in later epochs. The scarcity of substructures could influence galaxy formation and evolution. These discoveries from the James Webb Space Telescope are prompting cosmologists to re-examine dark matter models. A growing number of researchers are considering the possibility that fundamental assumptions of the standard cold dark matter model may need revision. Some research teams are exploring whether interactions between dark matter and ordinary matter might exist beyond gravity, or whether dark matter particles themselves possess more complex properties that could manifest more prominently under the extreme conditions of the early universe. Another intriguing possibility is that dark matter may consist of multiple components, with certain constituents aggregating more efficiently in the early universe, while others only become active later. This multi-component dark matter model could explain the observed temporal evolution characteristics, precise measurements of dark matter halos in the early universe. Also offer new opportunities to distinguish between different dark matter models. By comparing dark matter distributions at different redshifts, we can test various theoretical predictions. Of particular significance is that Webb's observations begin to impose new constraints on the mass of dark matter particles. If dark matter is indeed warm, these particles must possess sufficient mass to form the observed early structures. These discoveries regarding anomalous dark matter behavior in the early universe not only challenge our understanding of dark matter itself, but compel us to rethink the entire landscape of cosmic structure formation. If dark matter could rapidly form massive structures in the early universe, then the entire evolutionary history of the universe may need rewriting. The timeline of structure formation may need significant advancement, and the physical conditions of the early universe may require reassessment. When we gaze upon these early universe dark matter distribution data provided by Webb, we are actually peering into the behavior of the universe's most fundamental building blocks. Each data point narrates a story of dark matter during the cosmic dawn, and these stories are evidently far more complex and fascinating than we previously imagined. This realization will guide us toward a deeper understanding of the universe's material composition. Perhaps behind the veil of dark matter's mystery lie new physical laws beyond the standard model, awaiting our discovery and interpretation. As Webb continues to gather more data, our understanding of dark matter in the early universe will continue to deepen. Each new observation may bring fresh surprises and challenges. In this exploration, we are gradually unveiling the nature of dark matter and its role in cosmic evolution. Resolving this question is not only about understanding dark matter itself, but also about establishing the very foundations of cosmology. For dark matter is not only the primary material component of the universe, but also the key force driving the formation of cosmic structures. In future research, we must integrate multiple observational methods, from gravitational lensing to galaxy dynamics, from cosmic microwave background to galaxy cluster observations, to collectively construct a comprehensive evolutionary picture of dark matter. The Webb telescope's observations have opened a new window, allowing us to directly glimpse the distribution of dark matter in the early universe. This window will continue to expand, bringing unprecedented discoveries. In this process, we may need to abandon some traditional assumptions and embrace a more complex physical reality. Yet this very challenge embodies the allure of scientific exploration, advancing through challenges, breaking through confusion, ultimately reaching deeper understanding. The solution to the dark matter puzzle may lie just ahead, awaiting our discovery. Every advancement in observation, every breakthrough in theory, propels us closer to this goal. The latest numerical simulations indicate that the anomalous behavior of dark matter in the early universe may be closely tied to its formation mechanism. If dark matter indeed emerged in the cosmic infancy, its initial conditions could have dictated its subsequent evolutionary path. Some theoretical physicists propose that dark matter acquired its distinctive density distribution during cosmic inflation. This primordial distribution pattern enabled dark matter to rapidly form the observed massive structures. Once the universe began expanding, another possibility is dark matter coupled with other fields in the early universe. This coupling gradually weakened as the universe cooled, but significantly influenced dark matter's aggregation behavior in the primordial era. Notably, the hypothesis that dark matter may not be a single component substance. If dark matter consists of particles with varying masses, lighter components might have diffused more readily in the early universe, while heavier components rapidly aggregated. This mass stratification could explain the observed anomalous density distributions. Studies on the mass ratio between early galaxies and dark matter halos also provide crucial clues. Webb's observations reveal that in certain early galaxies, the ratio of stellar mass to dark matter mass is unusually high. This may indicate that dark matter halos formed before the peak period of star formation. If confirmed, this discovery would revolutionize our understanding of galaxy formation sequences. Traditional models propose dark matter halos form first, followed by gas cooling within them to form stars. However, new observations may indicate these two processes are intertwined in more complex ways. The rotational properties of dark matter halos also warrant deeper investigation. By analyzing galaxy trajectories within dark matter halos, we can infer the overall angular momentum distribution of these halos. The angular momentum characteristics of dark matter halos in the early universe may differ from those in the modern cosmos. Additionally, the ellipticity distribution of dark matter halos is a crucial observational indicator. Theoretical predictions suggest dark matter halos should exhibit near-spherical symmetry. However, preliminary observations from Webb indicate early dark matter halos may possess higher ellipticity. If confirmed by subsequent observations, this phenomenon could indicate that dark matter in the early universe underwent distinct dynamical evolution processes, or was influenced by other forces. Precise measurements of the dark matter halo mass function can help distinguish between different dark matter models. If massive dark matter halos already existed in large numbers in the early universe, the cold dark matter, CDM, model may require significant revisions. Particularly intriguing is the potential connection between dark matter and neutrinos. As one of the known dark matter candidates, neutrinos move at near-light speeds in the modern universe, but may have exhibited different properties in the early cosmos. Some theoretical models propose that neutrinos in the early universe acquired reduced velocities through certain mechanisms, thereby participating more effectively in structure formation. This hypothesis requires further observational verification. As more observational data accumulates in the future, we will be able to construct a more precise evolutionary history of dark matter. From the cosmic dawn to the modern universe, the distribution and properties of dark matter may have undergone complex transformations. Understanding these changes requires not only astronomical observations, but also theoretical support from particle physics. Perhaps the very nature of dark matter lies hidden within these anomalous behaviors of the early universe, ultimately unraveling the mystery of dark matter. This may require next-generation, larger aperture space telescopes and deeper theoretical research. Yet James Webb has already charted our course by revealing unprecedented characteristics of dark matter behavior. In this grand exploration, each new discovery marks a vital milestone, and every theoretical breakthrough represents a quantum leap in humanity's understanding of the cosmos. The mysteries of dark matter will ultimately be unveiled, and the James Webb Space Telescope stands as a crucial guide on this journey. The cosmic web is the largest-scale structure in the universe, composed of filamentary structures dominated by dark matter. It connects galaxy clusters and superclusters, forming a vast network spanning hundreds of millions of light-years. This three-dimensional web constitutes the fundamental framework of the cosmos. Galaxies resemble jewels scattered along this framework, distributed along filamentary structures. At the intersections of these filaments, massive galaxy clusters form. According to the standard cosmological model, the formation of the cosmic web is an extremely slow process, beginning with tiny density fluctuations in the early universe. These fluctuations originated from quantum perturbations during the period of cosmic inflation. Under the influence of gravity, these minor fluctuations gradually amplified. Higher density regions attracted more matter through gravitational pull, while regions of lower density gradually became hollow. This process required billions of years to evolve into the complex cosmic web we observe today. Within the traditional theoretical framework, the distribution of matter in the early universe should have been relatively uniform. The cosmic web should have been in its nascent stage, with only the faintest filamentary structures beginning to emerge. Galaxies should have been randomly distributed, without forming distinct network structures. The cosmic web should have only just begun to weave itself, when the universe was 1 billion years old. However, observations from the James Webb Space Telescope have completely overturned this expectation. By precisely mapping the spatial distribution of distant galaxies, Webb discovered that mature cosmic web structures were already clearly visible. When the universe was less than 1 billion years old, galaxies were not randomly scattered across the cosmos, but aligned along distinct filamentary structures. These early cosmic filaments already exhibited considerable complexity, connecting multiple dense galaxy nodes. Even more astonishingly, by analyzing galaxy redshift data, Webb reconstructed the three-dimensional distribution of these primordial galaxies, revealing they were embedded within a highly organized network, whose overall architecture bears striking resemblance to the cosmic web of today, albeit on a much smaller scale. This implies the large-scale structure of the universe was largely established in the very early universe. The significance of this discovery can be understood through an analogy with urban development. Imagine a wilderness region just beginning to be developed. Following normal development planning, we should first see scattered farmhouses and small villages. Over centuries, a network of roads gradually emerges, ultimately forming a transportation system connecting major cities. However, Webb's observations reveal that even as this wilderness was just beginning to be developed, a well-developed highway network already existed, linking already established urban centers. This indicates that the entire region's development plan was largely completed at the very outset. Webb's observational methods include multiple correlation function analysis and topological structure studies. By statistically analyzing galaxy distribution patterns across different scales, scientists can reconstruct the three-dimensional structure of the cosmic web. In data from the early universe, they detected distinct filamentary structural features, whose statistical significance far exceeds the probability of random distribution. Particularly noteworthy is Webb's discovery of a massive filament spanning 300 million light-years, at an age of approximately 800 million years. This structure contains dozens of early galaxies, aligned along a distinct path. The density and maturity of this cosmic filament match those of similar structures observed in the modern universe, yet predate them by billions of years. This discovery has profound implications. for theories of cosmic structure formation. If the cosmic web was already largely formed at such an early stage, it implies that the efficiency of structure formation is far higher than previously imagined. Traditional models of structure formation may require introducing new physical mechanisms to explain this rapid web-weaving process. One possible explanation is that some unknown interaction existed in the early universe, accelerating the formation of the cosmic web. Another possibility is that the nature of dark matter, making it more prone to clump together in the early universe and form filamentary structures. Theories also suggest primordial black holes may have acted as seeds, facilitating rapid structure formation. From the perspective of observational cosmology, this discovery holds significant implications. The early maturity of the cosmic web implies that galaxy formation and evolution may have been profoundly influenced by their large-scale environment from the outset. Galaxies are not isolated entities evolving in isolation, but nodes embedded within the cosmic web from the very beginning. Further research also reveals that the structural features of these early cosmic filaments exhibit unexpected correlations with temperature fluctuations in the cosmic microwave background radiation. The directionality of the cosmic filaments observed by Webb appears to correspond to certain patterns in the microwave background radiation. This may suggest that the large-scale structure of the universe was already determined in the very early universe. The challenge to cosmological simulations is equally severe. Even the most advanced cosmological numerical simulations fail to reproduce the maturity of the early cosmic web observed by Webb. Even under the most extreme parameter settings, the cosmic web structures generated by simulations remain younger and less mature than actual observations. This conundrum compels theoretical physicists to re-examine models of early cosmic evolution, modifications to gravitational theory, or the introduction of new fields and interactions may be required to explain the rapid formation of cosmic structures. These observations from the James Webb Space Telescope offer a novel perspective on cosmic evolution. From this viewpoint, the large-scale structure of the universe is not the result of slow growth, but rather rapidly formed in the early cosmos through some mechanism. Subsequently, within this fundamental framework, it gradually enriched and evolved. When we analyze the data of these primordial cosmic filaments, we are essentially deciphering the deepest structural code of the universe. The distribution pattern of every galaxy narrates the story of the cosmic web's weaving, and the beginning of this story is evidently far earlier than we previously imagined, and far more remarkable. This realization compels us to rethink the very nature of cosmic structure formation. Perhaps in the very first moments of the universe's birth, the seeds of the entire cosmic structure were already sown. These seeds rapidly grew into the magnificent network supporting the entire cosmos. The early maturation of this network may have determined the entire process of galaxy formation and evolution, ultimately dictating our position within the universe. Recent research reveals that material flows within the early cosmic web may have been more efficient than in the modern universe. Along filamentary structures, gas and dark matter could rapidly flow toward nodes where galaxies clustered. This highly efficient material transport mechanism may explain the rapid formation of early galaxies. Particularly noteworthy is that the positions of nodes within the cosmic web appear to correspond to primordial quantum fluctuation patterns. This correspondence suggests that the largest scale structures in the universe may be rooted in the smallest quantum world. This cross-scale connection remains an area not yet fully understood by modern physics. Studies of cosmic web connectivity also yield fresh insights. The early cosmic web exhibits exceptionally high connectivity, with tighter links between nodes. This may have influenced interactions and material exchange processes between early galaxies. The timing of cosmic web formation is also crucial for understanding dark energy's nature. If the cosmic web largely formed in the extreme early universe, then dark energy's impact on structure formation may be smaller than previously thought, or its properties may require reassessment. Another intriguing avenue is studying the evolutionary history of the cosmic web. By comparing cosmic web structures at different redshifts, we can trace its evolution over time. The Webb telescope's observational data provides unprecedented temporal sampling density. The geometric properties of the cosmic web also hold vital information. The early cosmic web exhibits specific topological characteristics that may reflect the universe's initial conditions and subsequent evolutionary history. The thickness and density distribution of filament structures constitute another research focus. Filaments in the early universe appear finer and denser than theoretical predictions, suggesting that the matter within them underwent more efficient aggregation processes. The dynamical state of node regions also warrants in-depth investigation. The velocity distribution of galaxies at early cosmic web nodes exhibits distinctive patterns that may reflect the merger history of dark matter halos and the evolution of gravitational potential wells. Cosmological web research also involves multi-messenger astronomy. By combining electromagnetic observations with gravitational wave detection, we may obtain a more complete picture of cosmological web dynamics. Future deeper observations will focus on several key directions: the physical state of gas within the cosmological web, the role of magnetic fields in filaments, and the interaction between the cosmological web and galactic feedback mechanisms. Theoretical developments required include more precise numerical simulation methods, improved hydrodynamic treatments, and more realistic galaxy formation models. Perhaps most crucially, we need to establish new theoretical frameworks to explain why the cosmic web formed so rapidly. Such frameworks may require integrating early universe physics, dark matter properties, and novel ideas in gravitational theory. Throughout this exploration, each new discovery reshapes our understanding of the cosmos. From the largest cosmic web structures to the smallest quantum fluctuations, we are gradually revealing profound connections across all cosmic scales. Observations from the James Webb Space Telescope have opened a new window, allowing us to glimpse how the universe's primordial framework formed. This window continues to expand, bringing more surprises and insights. With advances in data processing technology and the accumulation of observation time, we will be able to map the early cosmic web with unprecedented detail. These maps will not only show the distribution of galaxies, but also reveal the distribution of dark matter and the motion of gas. Particularly exciting is the possibility that Webb may discover even earlier cosmic web structures, from when the universe was only 500 million years old or younger. If a well-formed cosmic web already existed then, it would profoundly transform our understanding of the timescale for structure formation. The early maturation of the cosmic web also compels us to reconsider life's place in the cosmos. If cosmic structures formed so rapidly, then environments suitable for life may have emerged much earlier than we imagined. This holds significant implications for the search for extraterrestrial life. From a broader perspective, Cosmic web research will help us address fundamental questions about the origin of the universe, the nature of physical laws, and our position within the cosmos. Every advancement in observation, every breakthrough in theory, brings us closer to the answers to these questions. And the James Webb Space Telescope stands as a crucial milestone in this grand journey of exploration. Ultimately, we will construct a more complete picture of cosmic evolution, from quantum fluctuations to the cosmic web, from the earliest moments to today's complex structures. This panorama will reveal the entire process of the universe evolving from simplicity to complexity, from homogeneity to structured order. This exploration not only expands the frontiers of our knowledge, but also deepens our understanding of the laws of nature. In this sense, studying the early formation of the cosmic web is to pursue the deepest secrets of the universe and to explore the meaning of existence itself. Notably, the discovery of the early cosmic web has also transformed our understanding of dark matter distribution. Traditional models predicted dark matter should be relatively uniformly distributed. However, Webb's observations reveal dark matter is highly concentrated within the filamentary structures of the cosmic web, at levels far exceeding expectations. Studies of cosmic web nodes reveal intriguing phenomena. These nodes are not only sites of galaxy clustering, but also regions of heightened activity for supermassive black holes. This suggests cosmic web structures may influence black hole formation and growth. Another significant discovery is that galaxy distributions within the early cosmic web exhibits specific orientation patterns, where the rotational axes of galaxies often align with the direction of their host filaments. This correlation suggests the cosmic web exerts a profound influence on the galaxy formation process. Cosmic web research also incorporates the temporal dimension. Comparing its structure across different epochs reveals that filament evolution is not uniform, but rapidly forms in the early universe, before entering a relatively stable, slow evolution phase. This finding also offers insights into the cosmological constant problem. If structure formation was largely completed in the very early universe, the value of the cosmological constant may require reconsideration, or other as yet unrecognized cosmological components may exist. Research on voids within the cosmic web is equally significant. These vast voids are not merely regions of sparse matter, but may hold the key to understanding the nature of dark energy. The size and distribution of voids in the early cosmic web provide crucial constraints on cosmological parameters. Particularly noteworthy is the distinct evolutionary characteristics exhibited by galaxies within filamentary structures of the cosmic web, compared to those in isolated environments. This suggests that the large-scale environment exerts a decisive influence on galactic evolution. Future research will increasingly focus on multi-wavelength combined observations, integrating data across radio, optical, X-ray, and other wavelengths will construct a more comprehensive image of the cosmic web. Specifically, investigations into gas within filamentary structures will reveal how matter flows along the cosmic web. Theoretical models also require further development. Current models face significant challenges in describing the formation of the early cosmic web, potentially necessitating the introduction of new physical mechanisms or fundamental revisions to existing theories. Regarding observational technology, next-generation telescopes with larger apertures will provide more detailed cosmic web maps, particularly for detecting high-redshift cosmic web structures, which will directly test predictions from various theoretical models. Another crucial avenue in cosmic web research explores its relationship with the cosmic reionization process. The early cosmic web may have provided the fundamental framework for reionization, influencing the formation and expansion of ionized bubbles. Furthermore, studying the cosmic web may help us understand the fate of the universe. By tracing the evolutionary history of the cosmic web, we can better predict the future development of the cosmos. Within this vast research domain, each new discovery reshapes our understanding. Every theoretical breakthrough expands our horizons. The mysteries of the cosmic web are gradually being unveiled, and this process itself represents humanity's grand journey to comprehend the universe. Ultimately, we will discover that the cosmic web is not merely a structure of matter, but a witness to cosmic evolution, recording all history from the earliest moments to the present. To decipher this history is to understand the universe itself. In this sense, studying the early formation of the cosmic web is not merely exploring the past of the universe, but also seeking our place within it and the meaning of our existence. Every observation, every thought, brings us one step closer to this goal. And this is the most captivating aspect of scientific exploration. Cosmic expansion is one of the most fundamental and crucial concepts in modern cosmology. Its discovery fundamentally transformed humanity's understanding of the cosmos. In the early 20th century, Einstein predicted through general relativity that the universe might be expanding. Hubble then confirmed this astonishing fact through observation. The essence of cosmic expansion is the stretching of space itself. This expansion causes the distances between galaxies to continually increase, much like all points on the surface of an inflating balloon, moving away from one another. The redshift phenomenon is key to understanding cosmic expansion. When a light source moves away from an observer, the light waves it emits are stretched, shifting their wavelengths toward the red end of the spectrum. This phenomenon resembles the Doppler effect in sound waves. When a train moves away from us, the pitch of its whistle lowers. Similarly, when a galaxy recedes from us, the characteristic spectral lines in its light shift toward the red end. By measuring the extent of this shift, we can calculate the speed at which galaxies recede from us. Based on extensive observational data, scientists established Hubble's law to describe the rate of cosmic expansion. This law states that the speed at which galaxies recede is proportional to their distance. The proportionality constant is the famous Hubble constant. Precisely determining this constant has long been one of the most critical tasks in observational cosmology. Various measurement methods, from cosmic microwave background radiation to Cepheid variables, all strive to provide the most accurate value for the Hubble constant. In the standard cosmological model, cosmic expansion is considered uniform and isotropic, meaning that regardless of the observer's location in the universe, or the direction of observation, the expansion rate should be the same everywhere. This fundamental assumption is known as the cosmological principle, and forms the cornerstone of modern cosmology, underpinning our understanding of the universe's evolutionary history. However, observations from the James Webb Space Telescope are posing a serious challenge to this fundamental assumption. With unprecedented observational precision, the Webb telescope has uncovered a perplexing phenomenon. The expansion rate of the universe appears to exhibit systematic variations across different directions. These variations exceed the scope of measurement errors, suggesting that cosmic expansion may be more complex than previously imagined. Webb's observations reveal that galaxies in specific directions exhibit redshift values significantly deviating from theoretical predictions. This deviation is not randomly distributed, but follows distinct spatial patterns. It appears as if expansion occurs faster in certain cosmic directions than in others. If confirmed, this phenomenon would fundamentally reshape our understanding of the universe. The significance of this question can be illustrated through a vivid analogy. Imagine standing on the surface of a uniformly expanding balloon. According to theory, all points on the balloon's surface should recede from each other at the same rate. But if we observe points receding faster in certain directions, while others recede relatively slower, this indicates the balloon's expansion is not uniform, or that our understanding of its expansion contains a fundamental flaw. The Webb telescope's observational advantage lies in its unprecedented precision and sensitivity. It can measure the spectral characteristics of extremely distant celestial bodies, whose light has traveled billions of years to reach us, carrying precious information about the early history of the universe. Through precise analysis of these spectra, we can reconstruct the history of cosmic expansion and trace the evolutionary process of the universe. Particularly noteworthy is Webb's discovery during observations of high-redshift quasars that their absorption line systems exhibit complex structures. Different spectral lines from the same source sometimes exhibit slightly different redshift values. This phenomenon cannot be explained by simple cosmic expansion and may hint at new physical laws at work. Studies of internal dynamics within galaxy clusters also reveal new puzzles. Within the same cluster, the range of redshift values among different galaxies far exceeds what is expected based on gravitational interactions. This may indicate that the expansion properties of local space significantly diverge from those of the overall universe. This discrepancy cannot be fully explained by known physical laws. Another crucial discovery concerns the calibration of cosmic distance scales. Webb's observations reveal unexplained systematic differences between distances measured using different standard candles and those derived from redshifts. This discrepancy becomes more pronounced with increasing distance, suggesting fundamental flaws in our understanding of cosmic expansion. Theoretical physicists have proposed several possible explanations. One perspective suggests the nature of dark energy may be more complex than previously thought, could vary with time or spatial location. Such variable dark energy would cause inhomogeneities in the expansion rate, thereby explaining the observed redshift anomalies. Another possibility is that we need to modify gravitational theory. General relativity may require corrections on cosmic scales. Certain modified gravity theories predict cosmic expansion exhibits spatiotemporal variations, which aligns with Webb's observational findings. Though these theories require further observational data for validation, other scholars propose we may inhabit a unique region of the universe, where density differs from the cosmic average, causing locally observed expansion rates to diverge from the universe's overall expansion. This possibility prompts profound reflection on cosmological principles. From an observational technology perspective, research into this issue requires multifaceted evidence. Beyond traditional optical observations, data from multiple wavelengths, including radio and X-rays, must be integrated to construct a comprehensive cosmological picture. The multi-wavelength observation capabilities of the Webb telescope provide unique advantages for this research. Particularly noteworthy is the apparent tension between Webb's observational data and measurements of the cosmic microwave background radiation. This tension may hold key clues to understanding redshift anomalies. The high homogeneity of the early universe stands in stark contrast to the inhomogeneities exhibited by the later universe. Reanalysis of supernova data also reveals intriguing results. across different directions. The luminosity redshift relationship of type Ia supernovae shows subtle yet statistically significant variations. This may indicate that cosmic expansion is not entirely isotropic. If confirmed, this discovery would profoundly impact cosmology. Another research avenue explores the influence of large-scale cosmic structures. Giant superclusters and voids in the universe may perturb the expansion of local space. Such perturbations might have been overlooked in previous low-precision observations. Webb's high-precision observations now enable us to detect these subtle effects. As observational data accumulates, we may uncover more phenomena challenging existing theories. These phenomena could point to new physics, or demand significant revisions to current models. Regardless of the outcome, this represents a crucial advancement in humanity's understanding of the cosmos. Future research requires more sophisticated numerical simulations to understand the possible origins of these observed phenomena. Even the most advanced cosmological simulations today struggle to reproduce all the features detected by Webb. This suggests the potential need for new physical mechanisms, or fundamental improvements to existing models. Throughout this exploration, international collaboration proves crucial. It necessitates combining observational data from telescopes worldwide to eliminate potential systematic errors, to confirm the authenticity of the observed phenomena. Only through independent observational verification can we be certain of the validity of these discoveries. Of particular note is the study of redshift anomalies, which may be linked to other challenges in cosmology, such as the Hubble constant measurement crisis. Significant discrepancies exist between Hubble constant values derived from different methods, potentially related to inhomogeneities in cosmic expansion. Resolving one puzzle may aid in solving related problems. Research into the early universe also provides crucial clues. Precise measurements of the cosmic microwave background radiation reveal that the universe was highly homogeneous in its infancy. Why, then, did inhomogeneous expansion emerge during later evolution? This warrants in-depth investigation. Understanding this transition process may unlock the mysteries of cosmic evolution. Some theoretical models propose that primordial perturbations generated during the period of cosmic inflation could have amplified during subsequent evolution, leading to the inhomogeneities observed today. This possibility requires verification through more precise observations. The observational data from the James Webb Space Telescope offers a valuable opportunity to test these theories. Another intriguing avenue is studying the history of cosmic expansion. By comparing expansion rates at different redshifts, we can reconstruct the evolutionary process of cosmic expansion. Webb's observations provide unprecedented data for this endeavor, particularly in high redshift regions. These data may reveal detailed aspects of the universe's expansion history. These studies hold not only theoretical significance, but also profound implications for understanding the ultimate fate of the universe. If cosmic expansion is indeed inhomogeneous, the future evolution of the universe may diverge from current predictions. Understanding the nature of cosmic expansion is central to our predictions about the universe's ultimate destiny. Throughout this exploration, each new discovery propels us forward. Though answers may not come swiftly, the process itself is profoundly meaningful. Every observation, every analysis, deepens our understanding of the cosmos. Observations from the James Webb Space Telescope have opened new vistas, revealing cosmic complexity far beyond imagination. This realization itself represents significant progress. It reminds us, nature is always more intricate and wondrous than we imagine. As technology advances, future, more powerful observational instruments will yield greater data to help unravel these cosmic puzzles. In this journey of exploration, we are not only learning the secrets of the universe, but also expanding the frontiers of human knowledge. This process itself embodies the value of scientific research. These boundaries are constantly being pushed forward. Each observation writes a new chapter in history. Every discovery reshapes our understanding. This is the very essence of scientific research, exploring the unknown, advancing amidst uncertainty. In future research, we must maintain an open mindset and prepare to accept answers that may be entirely unexpected. For history teaches us that nature is always more wondrous than we imagine. Preserving an open mindset is a crucial condition for scientific progress. The study of redshift anomalies is not merely a specialized topic, but also a vital step in humanity's understanding of the cosmos. On this journey, we are both observers and participants. We explore the universe while discovering ourselves. This dual process of cognition makes this research profoundly meaningful. Ultimately, these studies will help us answer fundamental questions about the nature of space-time, about the origin of the universe, about the meaning of existence. The answers to these questions may lie hidden within those precise observational data, awaiting our discovery and comprehension. Every meticulous measurement, every in-depth analysis propels us closer to truth. Though the path may be long, each step is profoundly valuable. This embodies the spirit of scientific exploration. The James Webb Space Telescope, as the pinnacle of human ingenuity, plays a pivotal role in this grand quest. Each of its discoveries enriches our cosmic understanding, while every observation expands the frontiers of our knowledge. In this sense, studying the mysteries of cosmic expansion is not only about exploring the external universe, but also about reflecting on humanity's own place within it. This dual exploration embodies the profound significance of scientific research. It helps us understand the universe and helps us understand ourselves. As research deepens, we may uncover more unexpected phenomena. These discoveries may challenge existing theories or open entirely new avenues of inquiry. Regardless of the outcome, this is an inevitable process of scientific progress. Throughout this journey, we must maintain patience and perseverance. Scientific exploration is often a lengthy endeavor, requiring the collective efforts of generations. Yet every advancement justifies our dedication. Ultimately, we believe, through relentless inquiry, humanity will unravel the cosmos mysteries and grasp the essence of cosmic expansion. This conviction propels us forward on science's path. This is the allure of science. This is the meaning of exploration. Before the boundless cosmos, we forever hold curiosity and awe, eternally pursuing deeper understanding. This process itself is the most beautiful scientific poem. Observations from the James Webb Space Telescope are converging into an astronomical revolution. This revolution compels us to re-examine physical laws once deemed immutable. Let us systematically review these groundbreaking discoveries. First, the anomalous premature maturity of galaxies. When the universe was merely 300 to 400 million years old, the Webb telescope observed fully formed massive galaxies. These galaxies possess galactic-scale masses, with distinct spiral arms and luminous bulges, and host hundreds of billions of stars, a scale that should have required billions of years to form. Even more astonishing is their evolutionary state. Spectral analysis reveals these early galaxies already contain abundant heavy elements, including oxygen, neon, and carbon, elements typically produced only through multiple generations of stellar evolution. Yet they were already widespread in the infancy of the universe. Next is the conundrum of supermassive black holes. At just 700 million years old, Webb discovered a quasar with a mass 800 million times that of the Sun. This object, designated J0313-1806, not only possesses immense mass, but is also undergoing violent accretion, outshining its host galaxy by thousands of times. According to traditional black hole formation theories, even if accreting at the maximum possible rate since the universe's birth, it would take nearly 10 billion years to reach such a mass. This temporal contradiction points to the possibility that we may have overlooked some crucial physical process. Discoveries in cosmic chemistry are equally perplexing. In galaxies with redshifts exceeding 10, Webb detected distinct signatures of heavy elements. Particularly the presence of iron requires specific types of supernova explosions, whose progenitor star evolution requires tens of millions of years. More complex is the detection of nitrogen, an element primarily produced by intermediate mass stars, requiring even longer evolutionary times. These chemical signatures collectively indicate that stellar evolution in the early universe may have proceeded far faster than our current understanding suggests. Anomalous dark matter behavior adds another dimension. Through precise measurements of gravitational lensing effects, scientists discovered dark matter halos surrounding early galaxies, whose mass and density far exceeded theoretical predictions. These dark matter halos appear to have formed instantaneously, with a maturity equivalent to structures that evolved over billions of years. Particularly noteworthy is the density distribution profile of these dark matter halos, which exhibits an unusually steep central slope. This may indicate that dark matter in the early universe possessed properties distinct from those in the modern cosmos. The premature weaving of the cosmic web may be the most astonishing discovery. When the universe was less than 1 billion years old, mature filamentary structures were already clearly visible. Galaxies aligned along these cosmic skeletons, forming a network spanning hundreds of millions of light-years. This finding is particularly perplexing because the formation of the cosmic web theoretically requires billions of years of gravitational evolution. Yet, in the early universe, it appears to have been woven instantaneously. Putting these discoveries together compels us to confront a fundamental question. Do the laws of physics remain constant throughout cosmic evolution? One cornerstone of modern physics is the constancy of physical constants. From Newton's era to Einstein's, this assumption underpinned all theoretical constructs. Yet Webb's observational data is now shaking this foundation. The extreme conditions of the early universe may have altered the manifestation of physical laws. During the first few 100 million years after the universe's birth, temperatures reached thousands of kelvins. Densities far exceeded any region in the modern cosmos. Under such extreme conditions, fundamental interactions may exhibit distinct properties. One possibility is that certain physical constants undergo slow evolution, such as the gravitational constant or the fine structure constant, possessing different values in the early universe. These minute variations could significantly impact structure formation. Another possibility is the existence of unknown interactions that have faded in the modern universe, but dominated the early cosmos. These could have accelerated matter aggregation and spurred rapid structural formation. String theory offers an intriguing explanation. It predicts extra dimensions may have existed in the early universe. that gradually contracted as the cosmos expanded. Energy released during this contraction could have provided additional impetus for structure formation. The theory of inflation may also hold answers. The unique behavior of the inflationary field in the early universe could have generated a propulsive force that accelerated matter aggregation and structure formation. Modifying gravitational theory warrants equal attention. General relativity may require certain modifications on cosmic scales, particularly in the high-energy environment of the early universe, where gravity might exhibit distinct properties. The nature of dark matter could be pivotal. If dark matter possesses self-interacting properties, or exists in a different state in the early universe, this could explain the observed anomalous concentrations. It is worth noting that these theoretical conjectures require rigorous testing. Scientific progress advances through the cyclical interplay of bold hypotheses and rigorous verification. The value of the James Webb Space Telescope lies in providing an experimental platform to test these theories. By comparing physical phenomena at different redshifts, we can trace the evolutionary history of physical laws. Analysis of the chemical composition of the early universe is particularly crucial. The ratios of certain isotopes are sensitive to nuclear reaction rates. These ratios may preserve the physical fingerprints of the early cosmos. By studying these chemical signatures, we might reconstruct the physical environment of that era. Dynamics of galaxies also offer clues. If the rotation curves of early galaxies systematically differ from those of modern galaxies, it could indicate a change in the gravitational constant, or an evolution in the properties of dark matter. Precise measurements of the cosmic microwave background radiation, combined with Webb's observational results, may unveil further mysteries. The stark contrast between the early universe's high homogeneity and the inhomogeneities observed later warrants particularly in-depth investigation. Scientists are developing new analytical methods to detect subtle effects within vast datasets. These include statistically analyzing galaxy mass functions across different eras, examining the mass relationship between black holes and their host galaxies, and studying the evolutionary history of the cosmic web structure. These investigations require not only observational data, but also breakthroughs in theoretical models. Even the most advanced numerical simulations struggle to reproduce all features detected by Webb, suggesting the potential need for novel physical mechanisms. Even if physical laws prove eternally constant, Webb's discoveries compel us to address how the universe achieved such efficient structure formation within existing physical frameworks. Resolving this question will equally deepen our cosmic understanding. The history of science teaches us that every challenge to fundamental assumptions precedes theoretical breakthroughs. From Copernicus to Einstein, this has always been the case. The discoveries of the James Webb Space Telescope have elevated the study of early cosmic structure formation to the level of fundamental physics. We are not merely investigating the history of the universe, but exploring the essence of physical laws. In this journey of exploration, every anomalous data point, every theoretical impasse, serves as a stepping stone toward deeper understanding. Regardless of where the final answers lead, we will have taken a significant stride on the path to comprehending the cosmos. This is the very essence of scientific inquiry. Between certainty and uncertainty, between the known and the unknown, humanity's frontier of knowledge continually expands. The Webb telescope's observations are merely the beginning. As more data accumulates, we may uncover more unexpected phenomena that could guide us toward entirely new realms of physics. Throughout this journey, we must maintain an open mind, ready to embrace discoveries that may reshape our worldview. For history has repeatedly shown that nature's mysteries are always deeper than we imagine. Studying the early universe concerns not only its past, but also its future. Understanding the physical laws governing the cosmos' infancy may help us predict its ultimate fate. In this sense, the observations from the James Webb Space Telescope are not merely looking back in time, but also helping us comprehend the complete historical panorama of the universe. Every precise observation, every in-depth analysis contributes to this grand objective. This is the very essence of scientific research. In future explorations, we may need to establish entirely new theoretical frameworks. Such frameworks could unify the extreme physics of the early universe with the observational characteristics of the modern cosmos, providing a more complete picture of cosmic evolution. This quest may demand the efforts of generations, yet every step forward warrants our full passion and intellect, for it unravels the fundamental laws of the cosmos and expands the frontiers of human understanding. Ultimately, we believe, through relentless inquiry, humanity will unravel these cosmic enigmas and grasp the essence of physical laws. This conviction propels us forward on science's path. This is the allure of science. This is the meaning of exploration. Before the infinite mysteries of the cosmos, we forever maintain awe and curiosity, forever pursuing deeper understanding. This process itself is the most beautiful poem of science. When confronted with these cosmic-scale unsolved mysteries, our initial reaction may be confusion or even unease. The very foundations upon which we understand the world seem to be shaking. Those cosmic laws once held with absolute certainty now carry question marks. This upheaval in our understanding may indeed bring temporary discomfort. But allow me to invite you to shift your perspective. View these puzzles as gifts bestowed upon us by the cosmos. The very fact that we live in an era capable of posing these questions is an extraordinary stroke of luck. Imagine this. Amidst the vast expanse of human history, we are the first generation to truly glimpse the cosmos in its infancy. At this very moment, you might be sitting in your home or lying in a comfortable bed, holding a mobile device, surrounded by familiar daily surroundings. Yet beyond your immediate perception lies the observable universe spanning 96 billion light-years, containing 2 trillion galaxies, each containing hundreds of billions of stars. This fact alone is staggering. Let's do a simple calculation. If each galaxy contains an average of 100 billion stars, then the total number of stars in the universe would be an unimaginable figure. Faced with such colossal scale, our existence seems so insignificant, yet so precious. Your worries today, the challenges you're facing, your anxieties about the future, all find their proper place in the 13.8 billion-year history of the universe. This realization brings not a sense of insignificance, but a peculiar sense of release. Our everyday anxieties, viewed against the cosmic scale, gain a whole new perspective. Those questions that keep you awake at night, whether work pressures, troubles in relationships, or uncertainties about the future, when examined against the backdrop of cosmic evolution, take on a different appearance. This isn't to dismiss the importance of your feelings, but to offer you a grander frame of reference. Every discovery made by the James Webb Space Telescope tells us the universe is more wondrous than we ever imagined. This wonder is not a threat, but a precious gift. It invites us to step outside our daily mental frameworks and view existence itself through a broader lens. You need not solve all these cosmic puzzles immediately. In truth, no one can do so alone. Science is the crystallization of collective wisdom, requiring the collaborative efforts of generations. Your current curiosity and engagement with these questions itself constitutes a valuable part of this exploration, shifting attention from inner turmoil to pure wonder about the external cosmos represents a transformation in mental state. When immersed in contemplating cosmic mysteries, our consciousness naturally enters a tranquil state, where everyday worries recede into the background. This shift in state holds tangible value. It grants our brains respite, creating space for creative thinking. Many scientists have noted their most profound insights often emerge during moments of relaxation and contemplation. When the mind detaches from specific problems, solutions tend to surface naturally. You needn't be an astrophysicist to benefit from this perspective shift. Simply allow yourself to occasionally look up, gaze at the stars, or ponder the profound mysteries of the cosmos. This simple act can bring inner peace. Imagine that right now photons are traveling from distant galaxies, crossing billions of light years to finally reach your eyes. On their journey, these photons have witnessed the evolutionary history of the universe. They traversed the void between galaxies, navigated around dark matter structures, and ultimately met your retina. What wonders this journey holds! We are made of stardust. Every atom within us originated deep inside some ancient star. We are, in essence, the universe's way of knowing itself. This realization alone offers profound comfort. The next time you feel anxious or troubled, remember this: in the distant depths of the cosmos, galaxies matured within their first few 100 million years. Black holes grew into colossal beasts in unimaginably short times. Cosmic filaments were woven at the dawn of time. These truths remind us, reality is always richer than we imagine. In this universe brimming with unknowns, our very existence is a miracle. We are made of stardust, capable of contemplating the universe's origins, capable of being moved by beauty, capable of love and compassion. These abilities in the cold cosmos seem so uniquely warm. Let us hold onto this sense of wonder. Without succumbing to anxiety, the universe's mysteries will gradually unfold, and in this process, we may find our own peace. Now, close your eyes, take a deep breath, feel the breath flowing through your body. Imagine yourself floating in the cosmos. All worries and troubles dissolve like stardust. You are part of this universe, and the universe is part of you. This connection transcends time and space. With every breath, you resonate with the entire cosmos. Those unresolved cosmic puzzles are not riddles meant to trouble us, but opportunities to guide our thinking. They remind us that life's meaning lies not only in finding answers, but in preserving the courage to remain curious and explore. In this moment, let all thoughts slow down. As serene as the universe's expansion, as tranquil as starlight traversing the void. You need not solve anything, need not prove anything. Simply exist, simply feel. This is the gift the universe offers us. In the boundless expanse of time and space, we happen to meet at this very moment, on this beautiful planet. Possessing the capacity to think is itself the most moving miracle. Let us carry this awareness to continue life's journey, never forgetting to gaze upward at the stars, yet remembering to walk with grounded feet, between the vast and the minute, between eternity and the fleeting moment. Find inner balance and tranquility. This is the other side of science. It brings not only knowledge, but also wisdom. It expands not just understanding, but nourishes the soul. In this sense, Every cosmic enigma is a stairway to inner peace. May you, in this journey of exploration, find your own answers and discover inner peace. For ultimately, to know the universe is to know oneself. To explore the stars is to explore the heart. In this vast and mysterious cosmos, may we all maintain our curiosity, preserve our sense of awe, and keep our inner tranquility. For this is life's most beautiful state, to exist peacefully, between knowing and not knowing, between certainty and uncertainty. Now gently bring your awareness back to this room. Feel each point where your body meets the mattress. Notice the soft touch of your ankles against the sheets. Feel the muscles in your calves gradually relax. Your knees sink naturally into the support. The weight of your thighs fully surrenders to the bed. The pelvic area begins to relax. The muscles in your lower back slowly unwind. Pressure releases vertebra by vertebra along your spine. Your back molds perfectly to the bed. Tension between your shoulder blades gradually dissipates. Your shoulders sink naturally downward. Your arms rest loosely at your sides. Your elbows bend slightly. Your wrists feel relaxed and free. Your fingers unfold as gently as feathers. Now shift your attention to the neck and head. Feel the weight of your head fully supported by the pillow. The muscles at the back of your neck slowly relax. Your scalp begins to unwind. Your forehead smooths out. The muscles around your eyes gently release. Your cheek muscles naturally sag. Your jaw slightly loosens. Your lips softly close. Now begin to observe the rhythm of your breath. No need to deliberately alter it. Simply watch the natural flow of air. Feel the coolness of the air as it passes through your nostrils, enters your throat, fills your lungs, and then slowly exits. Let your breath gradually become deep and steady, as unhurried as the expansion of the universe. With each inhale, it's as if you're drawing in the stillness of the cosmos. With each exhale, you release the tension from your body. Imagine distant galaxies, spinning silently in the profound cosmos. Their existence requires no concern from you. Their motion depends not on your thoughts. They simply follow the fundamental laws of the universe, performing an eternal dance in absolute stillness. Feel those mysterious black holes. Though possessing power to devour all, they fulfill their duty only in the distant depths of space. They will not disturb your peace. Instead, through their eternal presence, they bear witness to the cosmos' stability and order. Perceive the invisible web of dark matter. Though we cannot see it directly, it exists as firmly as the universe's skeletal framework, silently sustaining the cosmos' structure. Much like the unseen supportive forces in your life, always holding you up from behind. Let your breath synchronize with the pulse of the universe. Each inhalation connects to the birth of stars. Each exhalation echoes the fading of starlight. Within this rhythm, find inner tranquility. Your arms grow heavier and heavier, as if immersed in warm stardust. Your legs gradually lose all tension, as if floating in zero-gravity space. Your torso relaxes completely, as if merging into the embrace of the cosmos. Neck and head fully supported by the pillow, requiring no effort, like an astronaut in space, allowing the gentle guidance of cosmic forces. Every muscle in your face relaxes. The frown lines between your brows slowly smooth. Tension at the corners of your eyes gradually dissipates. The formation and evolution of galaxies, the growth and silence of black holes, the weaving and expansion of the cosmic web. All these grand processes proceed orderly beyond your awareness. They require no participation from you, only wish for you to sleep peacefully. Those unresolved cosmic mysteries now transform into a silent lullaby, pervading like the cosmic microwave background radiation, gently enveloping your consciousness with the primordial tranquility and serenity of the universe. Imagine yourself floating in serene space, surrounded by countless tender starlights, each whispering softly, narrating the ancient tales of the cosmos. These stories need not be understood, only felt. Let sleep envelop you as gently as dark matter. Let dreams descend as softly as light from distant galaxies. Let the night's tranquility be as pure and complete as the vacuum of space. You have completed today's exploration. Now you may release all thought, release all questions, release all expectations. Simply immerse yourself in the essence of being. Let the power of the universe guide you into profound rest. In this moment, you become one with the cosmos. Your breath is the breath of the universe. Your stillness is the stillness of the universe. Your existence is part of cosmic consciousness. Within this union, find the deepest peace. May you find in the embrace of the cosmos the sweetest sleep, the most tranquil dreams, and the most complete renewal. May starlight keep vigil for you. May the rhythm of the cosmos lull you to sleep. May you find finite peace within infinite spacetime. Good night, dear cosmic traveler. May the stars guard your slumber. May the universe's stillness fill every cell. May you awaken with peace and wisdom bestowed by the cosmos, to continue this wondrous journey in the new day. Now, let consciousness slowly fade. Let thoughts gently dissipate, like starlight merging into dawn, like ripples settling upon the water. In this absolute stillness, sink into the deepest slumber. The universe sings your lullaby with the rhythm of gravitational waves, with the tenderness of starlight, with the embrace of dark matter. Let all this carry you into sweet dreams. Sleep now begins, as natural as the Big Bang, as eternal as the spinning of galaxies. In this moment of wonder, sleep peacefully, blessed by the cosmos. Enter the tranquil night. May your dreams shine as brightly as the Milky Way. May your sleep be as deep as a black hole. May your awakening be as radiant as a supernova. In this infinite cosmos, you possess this corner of peace. In this eternal time, you hold this moment of rest. Let everything slow down, quiet down, settle down. Good night, child of the universe. May you find the sweetest repose under the stars' watchful care. When you awaken tomorrow, bearing the cosmos blessing, embrace the new dawn.